All right, so next speaker is Alessio Lapponi, who'll talk about relativistic quantum communication between harmonic oscillator detectors. Alessio, please, the floor is yours.
Thank you, Rick, and good morning, everybody. Yeah, as I said, I'm Alessio Lapponi, third year PhD student in the Scuola Superiore Meridionale in Naples. I have to update my RQI account as well because of the affiliation, but it's okay. Okay, basically, I want to talk about the communication between harmonic oscillator detectors, and this talk is mainly based on a paper I published in June of this year with Dimitris Moustos, Professor Bruschi, and Professor Mancini from the University of Camerino. But beside that, I'd like to share with you even further results I've obtained. So, summarizing, I'm considering two static detectors in a 3+1 dimensional Minkowski background. And basically, the protocol is Alice that wants to share its state to Bob via a massless scalar field. I'd like to show you how the communication between these two harmonic oscillators can be recognized as a Bosonic Gaussian channel, in particular as a one-mode Bosonic Gaussian channel. And secondly, I'd like to show you that the properties of this channel can be studied even beyond perturbation theory, without considering any particular situation, such as delta-like interactions between the detector and the field, or gapless detectors. So let's, without further ado, let's describe the model. Okay, I'm not talking about particle detector models because I think that people from the University of Waterloo and Nottingham have already done that enough. However, just to resume, particle detector model will consist on a non-relativistic quantum system coupling with a field observable in general. In our case, I'm considering two particle detectors, and the quantum system representing them is a one-dimensional harmonic oscillator, or an analogous system, whose Hamiltonian is given by this. The scalar field is massless, as I said, and in that case, the interaction Hamiltonian will consist on a coupling constant, a switching in function, and then a tensorial product, let's say, between an observable proper of the detector and an observable of the field. As a switching in, I'm considering a sharp switching in. So basically, I'm considering that both the detectors interacts with the field at a time t equal to 0, and then the interaction remains constant afterwards. As the observable of the detector, I'm considering an analog of the position operator, let's say, of the one-dimensional oscillator. As a field observable, I'm considering the field operator, but with a Gaussian smearing. In this way, it's like considering the two detectors to have a Gaussian profile in space. Since we are talking about two static detectors, we don't expect any change on this shape, since the two detectors are static. Okay. How will they communicate? Well, it's simple. Alice prepares state its detector in a certain state, then coupling with the field, Alice shares some information with the field, then the field propagates to Bob's detector, and Bob interacting with the field will receive part at least of Alice's message. Since we are dealing with two harmonic oscillators, the whole system could be considered as a two-mode Gaussian state. All the entropic quantities of Gaussian states could be defined through the covariance matrix of the state. In case of a two-mode Gaussian state, we have the following expression, where sigma A represents the state of Alice's detector, sigma BB the one of Bob's detector, while the off-diagonal block matrices represent the correlations between Alice and Bob's detector. The quantum channel is then the one mapping the input to the output. As input, I'm considering the state of Alice's detector at the time t equal to 0, so before the interaction with the field, while as an output, I'm considering the state of Bob's detector after a time t, after the interaction with the field has started, basically. Now, the trick to find non-perturbative solution is basically to recognize the complete Hamiltonian of the system, which is this one, as the same of the one of two oscillators in a buffer of particles undergoing a quantum Brownian motion. In that case, the field plays the role basically of a ohmic environment. In that case, the Heisenberg evolution of the moment operator of the detector is given by the quantum Langevin equation. In particular, we have a coupled quantum Langevin equation. Let's say the evolution of the moment operator of Alice is influenced by the wine of Bob through this element here, which is the dissipation kernel, which is a 2 times 2 matrix in that case. And in particular, the off-diagonal elements of this dissipation kernel is proportional to the commutator between the field operator in Alice's position and the field operator in Bob's position. And obviously, we know that this commutator gives the causality of the problem. So if this commutator is 0, there is no causality, and so there is no influence between Alice's moment operator and Bob's moment operator. Now the aim is to compute this coupled quantum Langevin equation, and we can do that. An easy way to do that, and at least to compute the communication properties of the channel, is via the green function matrix. In particular, by defining this green function, which will be the solution of the homogeneous quantum Langevin equation, we got this expression for the moment operator, and this is very important because it allows to write Bob's moment operator and its time derivative in terms of Alice's moment operator at the time 0. But this means basically to express the output covariance matrix in terms of the input covariance matrix, and that's exactly what we want to build a quantum channel. The expression linking the output and the input will be this one, and they are dependent basically on two matrices, the T matrix and the N matrix. In that case, the quantum channel is a one-mode Gaussian channel, whose properties are widely known from the literature. In particular, all the properties and even the capacities are defined by two elements. The determinant of the T matrix, this one, which is the transmissivity of the channel. What is the transmissivity? Well, basically it's, we can think on the transmissivity on the portion of input signal effectively arriving to the observer, to Bob. So sort of a transmission coefficient. Then we have the determinant of the N matrix, which gives the additive noise. In particular, this expression here, which is proportional to the determinant of the N matrix, gives the number of noisy particles effectively achieved to Bob. So to have a good quantum channel, obviously we should have a high transmissivity and low noise. And the capacities are entirely defined by these two elements, and now we will see that. What is capacity of a channel? Well, basically the definition of a capacity is the maximum rate of information, which could be or classical or quantum, that the channel is able to transmit reliably. The capacity of a channel is basically both classical and quantum capacity gives the capabilities of the communication of classical and quantum information. To make you understand better this concept, if the capacity of a channel is 0, then this means that it's impossible to transmit reliably information with the channel. If instead the capacity is different than 0, information could always be transmitted with arbitrarily low amount of error. However, how would we differentiate a low capacity with a great capacity? Well, if a channel has a low capacity, then it requires more time to transmit reliable communication. I quote time because as time I intend the number of times in which we have to use the channel to transmit the signal reliably. So obviously it's always better to have a high capacity in order to have a faster communication. Now, in our particular protocol, since we are considering two static detectors in a Minkowski background, in a Minkowski vacuum, we have that it's impossible to transmit quantum information, otherwise the no-cloning theorem is violated. However, the classical capacity of the channel is always different than 0. So without further ado, now we are going to calculate the classical capacity for this protocol. And we'll see some interesting things. To calculate it, we have to find the elements of the green function matrix I described before. And it is possible to find exact solutions for them in two particular cases. The underdamped case, so when the coupling is much smaller than this number, and this is analog to the perturbation theory with a low coupling perturbation, let's say. And even in the overdamped case, so it is possible to compute exactly the properties of the quantum channel, so the these green function matrices elements, even when the coupling is much larger than this number. So even when the coupling is arbitrarily large. And the overdamped case basically means that we are able to compute the quantum channel properties beyond perturbation theory. The only non-analytical results arises when we are going to consider the resonant case, so when the coupling is comparable to this number. Now we will see case to case what happens. Starting from the underdamped and overdamped case, we have the following plots. In the underdamped case, we get a transition period, which is in general proportional to 1 over the coupling. After this, we got the capacity to reach a peak in time, and then drops to 0 afterwards. In the overdamped case, instead, we have almost the opposite situation, namely that the capacity turns on smoothly, reaching an asymptotic value for high times, in late times. And this asymptotic value is given by this. Now, from the plot, we can observe some interesting things. Let's look, for example, to the underdamped plot. In that case, the more is the coupling, the more is the capacity, and that's expected, because obviously low couplings means no communication between means low communication between Alice detector and the field, and so obviously even from the field to Bob. However, in the underdamped case, we have the opposite situation, namely, contrary to what is expected, the more is the coupling, the lower is the capacity. Why this? That's where that could not be expected at first. But we have to take into account even the noise, because the more is the coupling, the more is also the noise that Bob achieves in the communication with the field. In that case, in the overdamped case, the increasing of the noise, how can I say, overcomes the increasing of the transmissivity, making the communication worse. So now, what is the best coupling? If it's not an arbitrarily high coupling, the best coupling we can choose for the communication, is there a finite value for it? The answer is yes, and we can find it in the resonant case. So in the range of values for the coupling in which it's not possible to find exact solutions. In that case, we have plots similar to that for the capacities, and the best situation is recognized in the dotted line, so where the capacity remains flat, let's say, after reaching a peak. This best case scenario is reached when the coupling is equal to this expression. Here, D is the distance between the detectors, omega is the energy gap of the detectors, and sigma is the effective size. Is there also an optimizing energy gap, so an optimizing frequency for the detectors to maximize the classical capacity? The answer is yes. In this 3D plot, indeed, by numerical calculation, I have found several the values for the optimizing frequency, so for the optimizing energy gap for different detector setups, so for different distance between the detector and for different sides of them. So basically the conclusion is that fixing some values of the distance and effective size of the detectors, it is possible to find values for the energy gap and decoupling that optimizes the communication. So let me conclude by discussing something and make you open questions, let's say. Basically, the first thing is that it is possible to study the capacity of the communication between two harmonic oscillator detectors even beyond perturbation theory. Because, as I said, in the overdamped case, we can choose a coupling arbitrarily high and we got exact solutions for the capacity. However, despite it, a huge value of the coupling is not the one we want. It's not the one which optimizes the classical. Unfortunately or luckily, to optimize the capacity, we need a finite value for the coupling. And I found this value as long as the optimizing frequency for the detector, so optimal coupling and energy gap for a plethora of detector setups. So I want to ask you, do we really need to go beyond perturbation theory? In the sense, this proves that we do not always need a huge detector field couplings to optimize the communication. So maybe even okay, maybe not a very low coupling, but neither a really high coupling is needed to reach the optimal communication between detectors because of the presence of the noise. The other question I want to raise is, could we find a better communication protocol? For now, the answer is yes. I found some ways to optimize it. For example, I found that the classical capacity increases if Bob's detector and the field interacts later than Alice and the field. If we delay the interaction between Bob's detector and the field, we got less noise in general, and so a better capacity. And really curious thing is that it seems that the transmissivity is proportional to the imaginary part of the Whiteman function of the field considered, while the additive noise is proportional to the real part of this Whiteman function. This could be a hint, for example, if one wants to find optimal capabilities even for other contexts. For example, I don't know, we can consider different dimensions of the spacetime, different smearing, different background spacetimes, and so on. And using this hint, let's say, maybe we can, I don't know, find some better protocols in different situations than the static case. Moreover, if we consider a non-isotropic background spacetime, then the no-cloning it is possible to communicate quantum messages without violating the no-cloning theorem. And in that case, we could have even a quantum capacity different than zero. And I'm actually working on that by considering accelerating detectors with the help of Professor Loke in the University of Nottingham. Then finally invite you for further details to check the reference paper. And finally, thank you for your attention.
Thank you so much, Alessio. So, great. Maybe we have time for one question from. So, does anyone from the Zoom audience have any questions? Okay, if not, I have a bunch of things that we should definitely discuss afterwards, to be honest, because I think that I can definitely provide you with some insight on the imaginary and real parts and things like this, I guess. But for now, I'd just like to ask you whether in your protocol, whether you can, whether you would be able to get the detectors entangled using this, and whether you have quantified this.
That's a good question. Let me take the. Well, basically, I don't know, but I expect obviously that there is no entanglement in the static case. In practice, we could calculate this off-diagonal elements for whatever initial state. I don't think that some entanglement arises in vacuum. If in vacuum, in the sense, if Alice and Bob starts with their detector in the ground state of the oscillator, I don't think it arises some environment. Otherwise, we would have entanglement harvesting in vacuum. However, we can calculate the correlations between the detectors there. I expected, however, to have both classical correlation that quantum correlation. However, if classical correlation are much higher than quantum ones, we don't have any entanglement. However, yeah, it is possible with this method, basically, by calculating these off-diagonal elements.
Because yeah, we just expect that if the two detectors are exchanging information with the field constantly, then at some point they would get to a stage where they have exchanged enough quantum information so that perhaps they would be entangled. But let me know if you take a look at
classical information. So I expect that at a certain point there is a strong classical correlation between them, but I don't think there is entanglement.
Right, definitely. Okay, great. So thank you so much, Alessio. Thank you again.